So I'd just like to say welcome to everyone to the Science of Pandemic Tech series. Just to introduce people, hang on. So this Pandemic Tech series is brought to you by myself from WeHealth and by Luca Ferretti from the Big Data Institute at the University of Oxford. He is waving at you. It is a monthly seminar series, and what we try to do is support public health and the tech sector by really introducing the best possible science. And we've covered a huge range of scientific topics. Science we define very broadly to be all forms of knowledge, and we realize that professionals are busy and don't have a lot of time to be reading preprints, and we hope to digest what's going on and in the pandemic tech sector, give you what you need to stay at the cutting edge of what's going on, what's coming in the future. So it's a forum for interdisciplinary discussion for those working on pandemic tech, whether from the tech side or from the public health side. I'm Joanna. I'm a mathematical modeler and data scientist who's been very involved in exposure notification technology, and it is indeed exposure notification that we're talking about today. In particular, are the Bluetooth that lies behind the current exposure notification, and then especially with Ramsey's talk, the Bluetooth that could lie behind future notification systems and also non-Bluetooth systems and what they would achieve. So we're talking about, what is the best way to sense proximity between people in a way that is useful and informative for contact tracing. And so our first speaker will be Amanda Wilson. I was incredibly privileged to meet Amanda as early as April 2020. It was a huge shortcut. Other people took another year to understand the subtleties of airborne disease and why 6 feet still matters even when something is airborne. I had it all explained to me by Amanda in April 2020, and it all made sense. And I am forever grateful to her clear insight at all stages. Her field is generally microbial exposure, quantitative microbial risk assessment. She's worked on all sorts of things from masks to risk scoring algorithms for exposure notification. I'm very happy to say that she's taken a faculty job back at my own university again, and I have her as a colleague there, where she continues to do awesome work on risk. Next speaker will be Karen Schiefelbein, and she, this pandemic brings all sorts of people together, and it was interesting to see the defense sector get involved from, in this case, MIT Lincoln Lab. But this time the enemy is not people, the enemy is just a virus, and that the defense sector can be mobilized to help with the fight, that we're all in this together. So that means there's only so much I can say about Karen's past work, because I don't really know. But in this case, she's been doing great work to help support the CDC assess these kinds of developments, and she'll be talking about those experiments. And finally, Ramsey Farragher, who is also a person who took me to school with great YouTube videos out there already, and brought me up to speed with Bluetooth, about which I previously knew nothing, and explained how it worked to me and what all the issues were, and everything I needed to know about Bluetooth. So I'm happy to bring him here so he can do the same for you, as well as tell you about things other than Bluetooth. Just a quick heads up about what next month is going to be. You can mark your calendar. We have a speaker from New Zealand, so it's going to be at a different time so that the speaker from New Zealand can get up early in the morning and join us. So it'll be late for those of you in Europe. But today we're really talking about proximity sensing, people who are in close proximity. Of course, COVID is airborne, and it can spread throughout any enclosed indoor space. And the next session will be about strategies for presence tracing and the different techniques that have been adopted in different places for doing that, for tracking people who are in the same indoor location, even if they were not in close proximity. But meantime, I will pass it over to Amanda to start talking about proximity sensing with Bluetooth.
Great, thank you, Joanna.
Oh, sorry, one more announcement first. that that we do not, the chat is blocked for participants, but the Q&A is open. So please put all your questions in the Q&A.
All right, thank you. My name is Amanda Wilson. I'll be presenting on environmental SARS-CoV-2 transmission and a risk-based approach in digital contact tracing. And I will say that I'm coming at this as a public health scientist, so I won't get into too many of the details of the technology, but the two presenters who are following me are much more of an expert in that topic. So I first wanted to describe some definitions. I know this is an overwhelming table, but I put these tables in here on purpose so that you have these for reference. I had the opportunity during my postdoc a few months ago to work with two industrial hygienists. One of them is an aerosol scientist, and we worked on a review paper where we looked for references for different definitions that have been heavily debated on science Twitter and in other circles. So in your own COVID-19 reading, you may be thinking, what's the difference between an aerosol and a droplet? And what does this mean for transmission? Why are people so upset about the use of one term versus another? And so I'm going to go into some of the specifics in the terminology here. The two I want to highlight on this page are aerosol and the droplet. So an aerosol is defined as a suspension of droplets or solid particles in a gas without reference to droplet or particle size. An infectious aerosol is an aerosol that's containing a pathogen. A droplet is just a liquid particle, and a droplet may be of any size. So in certain disciplines, they may use different definitions for aerosol and droplet, but these are the traditional definitions. And you can see how it already can get confusing. There's some overlap, but not 100% overlap in these definitions. So what does this mean for our definitions of transmission? When people talk about airborne transmission or hashtag COVID is airborne, what they're referring to is that infectious aerosols are in a respirable size range. And this has a specific size. So it's often termed droplet nuclei, and you'll see that terminology in the healthcare literature a lot. And this is aerosols with a diameter of less than 5 microns. Whereas droplet transmission refers to pathogen-laden droplets that spray or project onto the facial mucosal membranes of a susceptible person. Usually this is considered to be in close proximity, about less than 3 feet from an infectious person, and it involves droplets greater than 5 microns in size. So that size cutoff can be really important for determining how close do we need to be to somebody to actually get infected. One thing to note is that airborne transmission is often referring to what we call long-range aerosol transmission, or this idea that I could be on one side of the room, somebody could be in another side of the room, we're not talking to each other, facing each other, and one of us can still infect the other. But this doesn't negate the importance of short-range airborne transmission, which is infectious aerosols in a respirable size range, so that's small, less than 5 micron size, but we're still in close proximity. And so there's a number of different overlaps between these transmission routes, which also makes the conversation about the importance of these different transmission routes complicated. To give a visual, I found this figure that I really liked from Tang et al. From this year, where they're showing a few different routes of transmission. So these ballistic large droplets are generally greater than 100 microns in size, are the ones where someone sneezes or coughs right onto your face and you're like, oh, gross, right? That's what we're talking about when we're talking about ballistic large droplets. And because they're large, they typically drop to the floor within a short distance. When we're talking about short range aerosols, there's a higher concentration of these at a shorter range than at a long range. So distance still matters when it comes to aerosol transmission. There's a greater range of the sizes of aerosols at this close range than at the long range. Even though the concentration is still greater at a closer distance, that doesn't mean that you're totally out of the woods if you are far away from someone. Your risk is likely lower than if you're at a close range, but it can still be considerable. In terms of how these different transmission routes contribute to disease, it can be really difficult epidemiologically to determine, was it a fomite who made this person sick? Was it droplet? Was it inhalation? Was it a combination of all these different exposures that sent them over the edge? And so modeling can be a really useful tool to investigate how these different transmission routes are coming into play. There was a recent paper last year within a healthcare context. It was a modeling study where they demonstrated that the inhalation route is likely driving a lot of these infection risks as opposed to the droplet or contact route, where contact route is referring to the fomite route. In terms of epidemiological evidence, since I don't have too much time to go into detail, I wanted just to provide some quick snapshots of 2 papers that I think demonstrate the importance of aerosol or airborne transmission. One of them is about the Skagit Valley coral super spreading event, and another is about an outbreak in a restaurant where people were infected by someone who was sitting on the other side of the restaurant. So this made some people scratch their head, like, how could this be droplet transmission? And every day I'm seeing new papers being posted on Twitter by different aerosol scientists showing that short range and long range aerosols are something we need to be thinking about. So how does this relate to digital contact tracing? Well, I will compliment Joanna back and say I had the wonderful privilege of working with her and learning under her mentorship this past year. And we were thinking about how are we going to capture different transmission routes? What transmission route can the app currently capture? And so we were thinking about short range aerosols within this context. We used a quantitative microbial risk assessment approach, which typically has hazard identification, exposure assessment, dose response, and risk characterization. And the main pieces here that I'll be talking about are exposure assessment and dose response. So to get from an exposure to a dose, we're interested in a concentration in the air, we're interested in a duration of that interaction, and we're also interested in your inhalation rate, or the volume of air that you're breathing over a period of time. Some other important things to consider when we're translating that dose to a risk is the fraction of the community that's asymptomatic, the days post-exposure, the infectious shedding that occurred during the interaction, and this dose response curve, or a quantitative relationship between dose and some risk outcome, which in this case is probability of current or future infectiousness. So we had to think about what data are going to come from the app and what data are going to come from the literature. So from the digital contact tracing app, we had information about duration of the interaction, and there were some limitations around that I'll get into, the days post-exposure, and we could kind of get at concentration if we thought about what is a rough distance that these people were apart, and how infectious was the person who was infected during that interaction. So most of the things I'll be talking about from now on in the presentation are from this paper. So here's a reference if you want to get more details. I'm just going to be doing a very big picture look. So here's a figure from our paper that describes how different calibration pieces were used to inform this risk scoring algorithm. So the app is not considering each person's individual inhalation rate, but rather using that to inform some of the weights that we used for describing how durations at different distances are going to result in a dose. So some things we considered were doses at different distances, data from controlled experiments, a probability distribution of distance as a function of attenuation, and we're using a Monte Carlo approach to account for variability and uncertainty in some of these relationships. From the app side, we're thinking about transmission risk level, what this means for a transmission risk value, and using information about the transmission risk value combined with time spent at different distances to give us a dose that then gives us a risk based on calibration with known infection rates of household contacts. So in terms of the transmission risk values and how that relates to days relative to symptom onset, the top figure gives you a look into how that influences the final risk. So if you interact with someone who is likely more infectious during that interaction based on the time when they were symptomatic, then that's going to influence the risk estimate that you get in the end. This first part of the table shows one application for our risk outcome, which is how much time would be needed to trigger a 14-day quarantine. And you can see that if you are interacting with someone who's very infectious or has a higher transmission risk level, and you're likely at a closer range, which would relate to a smaller Bluetooth attenuation, then you need less time to trigger that risk threshold or to surpass that risk threshold. Whereas if you're dealing with someone who's likely less infectious and you're likely further away, your risk isn't zero, but you're going to have to spend a lot more time in that environment to reach the same risk. Another approach that was really interesting, and this was really Joanna's idea, and I thought it was a really interesting approach, was to look at this in another way, which is how many days of quarantine would be needed to drop below a risk threshold. So as opposed to just giving everyone a 14-day quarantine or saying no quarantine or yes, quarantine, it has to be 14 days, looking at, we have information about your probability of current or future infectiousness, and we have information about how that changes over time. So why not look at the number of days that would be needed in order for you to drop below a certain risk threshold? And these risk thresholds are flexible, which makes them easy to use. So a few other highlights of the flexibility of this type of risk approach. The first one on the left side is just a reiteration of what we saw in the previous table, where we can see how risk thresholds can be used to define a number of days of quarantine and how different interactions might trigger different numbers of days for quarantine. We can also explore how the fraction of the population assumed to be asymptomatic affects this number of days of quarantine needed to drop below a certain risk threshold, which means that this could be adapted really easily based on the fraction of asymptomatics that you're seeing in a population. And then finally, another interesting thing that, that we explored was how testing could change this information over time. So if we have information about a negative test, for example, we're not certain that you're not infectious, but this gives us more information about your probability of current or future infectiousness, which would drop the number of days you would need to drop below a certain risk threshold for quarantine. So this might be an incentive, say, hey, if you get tested and you have a negative test, that could reduce your amount of quarantine. So why is a risk endpoint useful? In my opinion, risk is easier to communicate than exposure or dose. If I walked up to someone in the general public and said, if you wear a mask, you can reduce the number of viral particles you inhale by 50%, that may not be as meaningful as something like you could reduce your risk by blank percent. It can give us more information to those who are exposed. So again, not just saying you were exposed, period, you should quarantine, but giving them information about where their risk may lie based on the information we have. You can set acceptable risk thresholds. And this is a common practice in public health. So I just gave an example of a risk threshold that's used by the US EPA to inform drinking water disinfection standards. And then again, more nuanced quarantine guidelines are possible. And I think that's an exciting area of future research. What's still needed? The major limitation of our work is that we're just considering these short range aerosols, but in order to consider long-range aerosol, a really important component would be not just measuring durations of close contact, but also occupancy of the same indoor space. So accounting for indoor versus outdoor. And here are my references, and I've provided my email there if you'd like to reach out. Thank you.
And so we'll just move on directly to Karen, and we'll have questions, because some people will answer questions that came up from others' talks. So Karen, if you'd like to share screens. And turn your video on if you can.
Hello, I started sharing the screen and lost my Zoom window for a second there. So here we are. Okay, can you see the screen?
Yes.
Okay, great. Thank you for the introduction earlier. Apologies for my scratchy voice. We're getting over those summer colds that are going around. But I'd like to pivot for a minute from the infectiousness work. We'll come back to that theme. I wanted to start just by explaining very quickly the background on how EN is working for those who may need a primer or a refresher. And then we'll talk about some work that we've done to assess the use of smartphones as a substitute for a COVID dosimeter, which was proposed at the start of the pandemic as a way to help slow the spread of the disease. So Alice and Bob, our canonical friends here, are both running exposure notifications, or perhaps a similar contact tracing service. Their phones emit special Bluetooth messages. We call these beacons. And those have anonymized text strings all day and all night. And EN is keeping track of the messages, their timestamps, and their contents, as well as the signal strength of each message. When Alice tests positive, she gets a one-time code from her public health department, and that allows her to upload information about the keys and messages, the keys and information about perhaps her date of symptom onset. That goes to a national server. And that date of symptom onset is included when other people's phones download the keys and check to see if they heard any of those random beacon messages that Alice's phone had generated from the keys. If they were too close for too long, as estimated by the signal strength and timestamps, then those folks are alerted to go get tested, perhaps quarantine, watch for symptoms, etc. If the system is set up well, and if it has enough users, then it works faster than manual contact tracing. It reaches farther than manual contact tracing, and it can keep working even when public health teams are overwhelmed, which we did see happening early on. So those of you who are familiar with Bluetooth are probably already wondering why anybody would be using that. And I know Ramsey is going to go into great detail on some of the pros and cons. What part of what we wanted to dig into early on was whether it was even worth trying Bluetooth as a distance estimator, and some of our early testing here at Lincoln last March showed that it was indeed worth a try, especially considering that COVID dosage doesn't adhere to a precise distance threshold itself. So we wanted to find out whether those mushy distance estimates from the Bluetooth signal strength are actually going to correspond well to a rough estimate of COVID dosage as well. Finally, part of the EN specification is this risk scoring algorithm that attempts to match that distance estimation up to a dose estimation. The Public Health Authority can define 4 bins or buckets for signal strength, and then weight each of those bins differently so that a close encounter is contributing more dose or more risk, as Amanda said, than a distant encounter. And then the infectiousness is also weighted by how close the encounter was in time to the date of symptom onset. There are certainly more refined ways of doing that, but this is the spec that we're working with today. The phone's Bluetooth data is used to estimate how many minutes the person spent in each distance bin, and then we get a weighted average of the exposure minutes. For the rest of these charts, I usually refer to that as the risk score. Finally, that is compared to an alert threshold that's set by the Public Health Authority. And if it exceeds the threshold, then the user is alerted and they're advised on next steps. So that risk scoring algorithm is mathematically simple and easy to implement, but choosing a set of weights and thresholds that's going to work well is actually a real optimization problem. And that's assuming you know what you want to optimize for. Each region is free to choose its own configuration, and most US states with exposure notifications have settled on one of 2 template configurations or something very close to them. The current implementation of EN allows for only one set of attenuation and infectiousness weights and thresholds for each region, but the health authorities do have more flexibility when it comes to having multiple alert thresholds, and if they choose different messages conveyed to the user based on their estimated risk level. And that's something that we're going to explore more in the data in a few minutes here. A little bit of context on the work that we've done within our program for the CDC. We were asked to assess the usefulness of automated contact tracing, and that includes everything from human factors and cybersecurity concerns to integration with public health workflows. But the part that I'll be talking about today is the work that we've done to understand how EN is performing on hardware. We've done several different data collections over the course of the year, and they've been all focused on answering one or more of these 3 questions. First, given the variety of the Bluetooth chips and drivers out in the field, is EN doing enough to calibrate the signal, or even with calibration, is it still too noisy from environmental effects? Number 2, how does the physical configuration of a pair of phones affect the sensor performance? And number 3, how does the logical configuration of the algorithm affect the sensor performance? There were a number of potential headaches that we needed to solve up front in order to do rigorous testing, but fortunately we knew that we could solve some of them in software, some in hardware, and the rest we could cope with using experimental design choices. So on the software side, the EN apps both enable and constrain your data collection. You need an app to drive the service, but it doesn't have access to the low-level beacon information. Normally, apps don't test for exposure on the same data more than once, but we wanted to evaluate different risk scoring configurations, so we would need to rerun the numbers. And fortunately, we were able to use those records that we logged on the phones to identify the sender of each beacon message and then build a tool to replay the risk scoring for all of our test scenarios mathematically after the physical experiments were done. And this was much faster than physically repeating the exposures, and you get a more accurate comparison of outcomes because you're running on the same scene over and over. Part of what we needed to do was to test at distances and durations that could cause a risky exposure, but we also needed to do this without asking our staff to take unnecessary risks before we had vaccines. So we used robots with mannequins that we had shown had similar radio frequency absorption characteristics to adult humans, and this really enabled the kind of tests we wanted to be able to perform. And finally, we care deeply about doing our tests rigorously, but the thing about testing the system is that in real life, it's held by people. And if we did everything very, very scripted and very constrained in terms of number of poses and angles, we were concerned that we weren't going to capture that broad range of actual human interactions. So we started with anechoic chamber tests to focus on fundamental performance characteristics in ideal conditions, and then we built up from there to admit more variation and more noise and approach more realistic situations. There really isn't time here to review all of the experiments and the results. So I want to give you the bottom line from the anechoic chamber and those low mobility tests, which is that there is a lot of noise in the Bluetooth data, and it is definitely affected by the orientation and the absorption from bodies. But remember that the real question is whether it's working as an estimator, not of distance, but of infection risk. And with the variation in the airflow around people, this might still be good enough. The important thing is that we collected the data to show what's happening at the lowest level of the system. And it suggests that if we had additional information about where the phone is, perhaps from other sensors on board the phone, some of that noise could be reduced. It also suggests that although a single signal strength measurement may be way off for its specific circumstances, the integrated risk estimates from multiple measurements may still be accurate enough to be useful. So now let's look at a set of experiments where we moved out of the lab and into the real world. We wanted to use as many phones as possible and vary the hardware, include several different models of Androids and iPhones. All of these scenarios had a mix of different carriage states, whether the phone is in a bag or a pocket or taped into a mannequin's hand. And where it was realistic, we had the mannequins change their positions and their orientation according to a script. We had about a month to carry out testing under COVID constraints. And since it can take up to half a day for 2 people to run a single 1-hour test due to the manual setup and the data exchanges between the phones, we wanted to be able to run 3 trials of each scenario as well. So in the interest of time, we focused on the ones that were the highest priority for our university partner. Although we were limited by the number of mannequins and staff and the number of phones we had available to include in each test, this was still going to be one of a very few experiments conducted worldwide to answer these questions at this point in time. And it's the only one that we know of that included a wide range of scenarios and phone models. So here is a brief visual tour of the different kinds of scenarios that we ran. Each of the academic ones were 45 minutes to an hour long. The lecture scenes were mostly static. People sat still during the lecture. And then the smaller workspace scene in the upper left had people moving around and collaborating on different projects. For public transit, we modeled a bus queue in which people arrived and left during a 30-minute wait for the bus. So we had some shorter interactions and some longer ones there. We used an MIT shuttle bus as well as the MBTA testing facility in Boston to collect data in 3 different public transit vehicles. And those were a couple of really long days, but it was nice to go and do something in a different place, different scenes. And if you ever need to do a data collection on a train, the T is a very nice place to work. They're very accommodating. Finally, we wrapped up this set of tests with 2 different parties, or at least party standards if you're a mannequin, I guess. I have a short video. I'm not going to be able to play the whole thing in the interest of time, but to hit on a few key points. The beginning of a test, we have to manually enable EN on all the phones. The sick phone is number 16 with a COVID symbol on top, the green hat, And each of these phones has a dosimeter floating over it with both a low threshold in yellow and a high threshold marked in red. If the dose stays in the green zone, then the user wouldn't see an alert at all the next day. If it crosses one of the thresholds, then they would see an alert message that corresponds to that lower or higher risk encounter. The iPhones don't give us the minute-by-minute data needed to show the accumulated exposure over time. So for this video, they don't have dosimeters. But I can tell you that at the end of this particular test scene, phone 17 alarmed low, or sorry, high, and phone 20 in the wheelchair alarmed low. So the sick person is moving around from cluster to cluster during the party, and some of the other robots move around as well towards the end of the scene. The humans were asked to stay on station, but move around a little bit and face in different directions, and then interact with the sick person when they come over. So as you can see, the numbers have been climbing for most of the phones. You might have also noticed that phones 6 and 8 aren't showing any exposure at all yet, and they won't by the end of the test. As it turns out, neither of those phones happen to hear a single beacon from the sick phone. That could be due to signal interference. It could be due to absorption. There is a laptop and a table in the line of sight between phone 16 and phone 6 there at that table. So the system isn't perfect, but given the social context here, we expect that those people would have been contacted either through conventional contact tracing or perhaps directly contacted by their friends, and that they would go and get tested anyway and modify their behavior appropriately. So remember that risk scoring algorithm. We could only run with a single configuration during the video I just showed you. But with all of the beacons that we logged, we can rerun that algorithm on the desktop. And that helps us predict the performance of different configurations by running it with any parameters you might want to try. We were also able in post-processing to expand the size of the exposure data set by an entire order of magnitude. We consider all the phone pairs rather than a single sick phone as exercised on the day of the test. So given that we have the ground truth data here, it's possible to calculate probability of detection, probability of false alarm. You can make ROC curves and DET curves, but I'm going to stay away from those today because we've found that a simple map of the probability of alert has been especially useful for conveying the system performance, kind of at a high level glance. We can plot this out on a contact grid with ground truth for distance and duration. And this allows us to hold that standard contact tracing metric, however you want to define it, in sight as a reference. And on these slides, it's still using the 6-foot, 15-minute reference from the CDC. You can still explore the space around that, the way we're looking at this. We all know that the too close for too long region is not a bright line in reality. And the public health authorities do understand this. They're interested in capturing the interactions within that box, but also paying attention to the region outside of it. So for an example of what we can do with this, I'd like to walk you through the performance of the risk scoring for all of our different scenarios from these real world tests, all combined. This is showing the configuration that was in use by the University of Arizona, for example, and we're going to compare how it behaves with two different thresholds. Now, on these, I'm only showing data where we actually have samples for interactions at specific durations and distances. It's not hard to build an interpolated and smoothed version of this, but I wanted to show you that the variation in there that we see without interpolating and smoothing it. This is showing the average risk scores, and the white cells are high risk, dark cells are low risk, and charcoal gray is just no data. You can see that there's a clear gradient overall as the distance is increasing and the duration is decreasing. Then once we apply that high threshold, it's no surprise that the gradient is still there, looking at the probability of alert. There's definitely some variation in the middle. If you look at around 30 odd feet and 55 to 60 minutes, you can see that it dips low and then comes back up a little bit. But when we dig into the numbers for the cells, the phones pairs that made up the encounters in those cells, we can see that those values are getting pulled higher due to having less obscuration, fewer phones in pockets, more phones in hands for those. And they're pulled lower in other cells by the converse effect. And it's possible to slice and dice this dozens of different ways. I'd be happy to talk through this more with folks another time if you're interested. Looking at the low threshold, you can predict that even more users would receive alerts, which is kind of a no-brainer. But it shows you where on the map those boundaries that you might be interested in are happening. Is this a good or bad setting for you? That really depends on what your region wants to do in terms of steering people towards testing or simply having more situational awareness about the types of encounters that they're having. If you are interested, we can certainly run with other models. We can, other configurations. We have other ways of analyzing this data that there isn't time to go into. But the takeaway is that although there are clearly better ways to measure distance than Bluetooth, the system that's deployed today can be configured to have a high probability of detecting the exposures that are highest risk and a lower probability of capturing the low risk ones with the information that is currently available on the phone. So in summary, when EN launched, there simply wasn't a body of work showing how well that risk scoring algorithm might be performing with the Bluetooth data that's available. We worked our way up from small and methodical repeatable exposure tests to larger and more dynamic ones with high quality ground truth, time and distance data. And these data sets are available for sharing, as well as some of our visualization tools are going up on GitHub. We've been able to feed this data into models that then help public health teams make decisions about how to deploy EN in the context of all their other mitigation strategies. It's not a perfect tool for the job, but it does help get the job done. I'm very much looking forward to hearing what Ramsey has to say next about Bluetooth and moving beyond the current implementation. But first, I want to say a very heartfelt thank you to everyone who was part of our test team here on site or who provided logistical and technical support from far away. This was tricky to pull off with so many moving parts and so few people being able to be present, but it was a real pleasure to work with all of you. And with that, I will hand it off to Ramsey. Thank you very much.
Thank you, Karen. Shall hopefully get this screen sharing right. Is that coming through okay? I hope so. Perfect, thank you. So yeah, I'm going to concentrate on all of the cool stuff that could be coming that we can add to Bluetooth. I'll talk about Bluetooth a little bit in the first couple of slides, but as Joanna mentioned, if you're a glutton for punishment and you put the right turns into YouTube, there's probably about 90 minutes of me across 3 different talks, I think, really digging into some Bluetooth stuff and all the real low-level issues and challenges. I'll give a quick summary now, and of course we can always take anything in the panel on any real low-level stuff about radio propagation issues. I'll just quickly cover why we're using Bluetooth today and what the challenges are, and then get on to some future things. So Bluetooth BLE version 4 is what we're using in the phones, and the reason we're using it is very much given away by the name. It's the lowest power way that your phone can say hello to another phone. And in fact, transmitting the Bluetooth energy is effectively a negligible drain on your battery. The phones can be pinging every 10 or 15 seconds all day long, and it barely impacts your battery life at all. Listening for the pings is actually the bit that's draining batteries, believe it or not, on phones when you're using contact tracing. And all of the processing, seeing if the message is there and you can receive it. It is a nice private technology that we can use. It has absolutely no needs to get any network information or go via anyone else. The 2 phones can simply say hello to each other, and they're the only 2 that know that a message was transferred over Bluetooth between them. But in terms of using Bluetooth to determine the range between 2 phones, it's not designed for that purpose. So if you gave an engineer and a physicist the task of taking a section of the 2.4 gigahertz radio spectrum and gave them a bandwidth and an allocation and said, build me the best thing you can, you could easily build something that can measure the range between two devices to within a centimeter. But that's just not what Bluetooth was designed for. It's not built into the protocol. There's no ranging measurement using time of flight or carrier phase measurements, the actual radio phase measurement itself. All we've got is a measurement of the signal power. And the signal power fluctuates wildly, not only because of objects getting in the way, but because the signal bounces off the ceiling, the floor, the wall, people, and at every location in a space, the signal is interfering with multiple copies of itself. And that can boost the power, and it can also dramatically reduce the power. And so it's very difficult, especially in an indoor environment, to use signal power as a measure of range, because the fluctuation is so high when it interferes with itself. And that's called multipath interference. And so there are, as I'll get to through the rest of this talk, there are other technologies that are more resistant to multipath interference. So signal strength, a very poor predictor of distance. And one of the challenges as well is that you can gather more measurements, gather more information to make an inference about what the signal strength really is, especially over time. But we do have this issue at the moment where there is the desire for some of the contact tracing apps to simply have the minimal impact on battery life possible. And that means they're gathering as little data as they can. And if you gather as little data as you can, then you're not making the best possible metric in order to assess exposure. And so it would be nice to see a slider bar of how much battery life am I willing to sacrifice today for my contact tracing app to be better, but we don't have that level of user settings in any of the apps at the moment. As we just saw in Corin's talk, and as I mentioned, the attenuation is very strong by the human body, and that's one of the challenges. So humans can block the signal and you don't get a good reading of that signal power because the body was in the way. But then the other issue is that we use these 2.4 gigahertz signals, Bluetooth and Wi-Fi, both in that band. We use them so much because they go straight through nice indoor building materials. They'll go straight through dry stone, they'll go through walls and plasterboard and wood. And so it's challenging because you can have two people in a completely separate airspace, and two phones can think they're really close, but in fact there's a wooden wall in the way, or one's downstairs and the other's upstairs and it's going through the floor, and so on. And so we'll look at some of the ways you can stop that issue using other sensors. And so in general, Bluetooth signal strength is not the best way to answer the question, are these two humans sharing the same air? Because Bluetooth transmission isn't going through the air, it's going through space and walls and wood and so on. So what else can we do? There's quite a lot of options actually in that smartphone. So we'll dig into all of the different things we could be using and some of the things that might be coming if we're still doing contact tracing, even in just a year's time. But certainly next time we have this pandemic, next time we have another one, we might be better prepared for all of the things we can bring to bear from inside our smartphones. The Bluetooth version 5 is actually in some of the latest generation smartphones. That has an angle of arrival feature for positioning, but it's the infrastructure side. So if people set up the equivalent of a Wi-Fi hotspot, but a Bluetooth kind of serving hotspot or a Bluetooth beacon in an environment, it's actually those parts of the infrastructure that can measure this extra information and understand bearings to the handsets. So the handsets themselves are not going to be able to do any clever new things between each other using Bluetooth 5 versus Bluetooth 4. And there's only a very small number of phones that have Bluetooth 5 in them at the moment as well anyway. Interesting enough, the first Samsung to have Bluetooth 5 in it had the chip in it, but the operating system didn't support it. So you were buying a phone with Bluetooth 5 thanks to the marketing, but you couldn't actually use it. But that's not the case anymore. The operating systems do support Bluetooth 5 today. I'm sure we're all very familiar with satellite positioning, the GPS chip in our smartphones. I'm pretty sure it's standard in all smartphones nowadays across the world, cheap or expensive. satellite positioning is not a great way to measure proximity per se. The accuracy can be highly variable. It can be 30 meters, 50 meters of error. And so it's not a great way to confirm if two devices are close together. And its primary use in contact tracing at the moment is to have that record as to where people have been and when, for the more kind of long-term understanding of how much an infected person might have moved around and where they were. We can't actually access the location information from your GPS chip if you're using the GAIN protocol, the Google Apple Exposure Notification Protocol, on a contact tracing app. So you can't combine those two together without workarounds at the moment. But the GPS chip can be used for other useful information. So visibility of the satellites and the signal strength of the satellites is actually quite a good metric for am I outside or am I inside? And as I'll discuss through the rest of this, there are other metrics we combine with it too. So it's a good way of simply determining if the probability that you think you're in an indoor or an outdoor space. And you could do that in a manner by which you don't actually access the position fix. So it is possible to ask the chip to tell you the signal strengths of the satellites it can see, but not return a position fix. Now that can't be done at the application level. You can't write an app that does that. But the operating system, Google or Apple, could happily create the ability for an indoor-outdoor metric to be provided that's giving you a score that you are indoors or outdoors without the location actually being calculated, just measuring the signal strength of different satellites. The other thing that you could do with GNSS positioning is determine if two devices are traveling together. So have a sequence of measurements over time and be able to weigh up the chance that two people were sat on the same bus, perhaps, versus two people were in different cars that are just sort of traveling kind of on the same journey down the same roads, but they're clearly not in the same vehicle because of the times you're moving and how much you're moving when. Another sensor that is in use for contact tracing already on the Novid app, I think that's the only one I'm aware of that it's in use of, is ultrasound. So this is using the microphone and the speaker in the phones to transmit a pulse beyond our audible range, and actually timing the transmission back and forth of these ultrasonic pings is a really good way of measuring range. So you can do this with an accuracy of just a few centimeters. Ultrasound is very strongly attenuated, stopped pretty much by glass, brick, wood, material, human bodies. So you've got the issue that it's again blocked by humans that could be in the way, blocking two phones that are actually close together, but it is giving you that extra level of protection against the false positives of two people sat either side of a pane of glass and a Bluetooth signal happily recording that you're very close to each other, but an ultrasound signal would not transfer between the two phones through a pane of glass or a wall or a floor or a ceiling. It is inherently private because when the phones talk to each other over ultrasound, you can filter out all of the audible range completely when you're doing the transmit and receive. And the pulse that you send, you only need to transmit tens of milliseconds of data, maybe half a second's worth of data. So the microphone would be open for such a small amount of time that you're not capturing private information, and you can filter the audible speaking section as well anyway. And I actually cobbled together a quick ultrasonic pulse in just about 20 minutes, just to demonstrate what it is. So transmitting a pulse out of my microphone's, my laptop's microphone, and then timing the echo coming back off the ceiling. And these are two screenshots of me just sort of holding the laptop on the ground and higher up. And you're seeing on the left of both of these, that loud pulse is the transmission, and then you're seeing the echo sometime later. The scale at the bottom is meters. I just didn't bother zeroing it. Don't worry about the fact that it doesn't start at 0. Don't worry about that. But you can see about 2 meters being recorded as a distance there, about 3 meters here. And the width of that pulse you're seeing there, which is down at the kind of centimeter level, is the resolution you could use to measure the distance to another device with ultrasound. And it didn't take me long to knock up a piece of code to do that. In fact, I spent longer arguing with people about whether ultrasound is a good idea for contact tracing than it took me to code this up and make these plots. UWB is quite an exciting technology for contact tracing. I think this is one of the ones that can make a big difference. It's coming on the latest generation iPhone and Samsung phones at the moment. Ultra wideband is referring to the amount of the radio spectrum that's being used. So this little graph, sorry, this little plot here is showing GPS is a very, very narrow signal in frequency space. It's only a couple of megahertz wide. Ultra wideband, the whole radio spectrum that's available for ultra wideband is many, many, many gigahertz wide. But the pulses that are used are typically 500 megahertz wide. So over 100 times more bandwidth than Bluetooth has or GPS has. And this means you can use these little radio pulses to make measurements at the kind of 5 centimeter level. Again, it's attenuated well by walls and other obstructions. It's part of a growing ecosystem because it's what's powering the new AirTag technology from Apple. So we're going to see a lot more UWB, I think, on smartphones, and this will be a good way to do ranging going forward for contact tracing. QR codes are used across the world to give a location fix instead of GPS. It can be much more accurate than GPS, and certainly you can put a QR code anywhere in an indoor space where GPS doesn't work and have a record of that location. The drawback with it could be the ease of kind of choosing not to gather that location information, or people actually messing with it and faking it, which hopefully they wouldn't do, but it's inherently not a high integrity way of determining location. Sensor fusion is when you gather fingerprints from lots of different sensor types together and combine them in one overall measurement. So there are lots of ways that we can make some simple measurements on a smartphone into a fingerprint and then compare fingerprints between different devices. So a simple example is opening the microphone for a second between two phones and then doing a spectrum analysis and confirming if both phones are hearing me talking right now at exactly the same time, or if another phone is through that ceiling above me and can't hear my voice. And you can do fingerprints across a range of sensors. Audio is just an obvious one, but light sensors are on a phone, barometers, all sorts of things can be used to generate fingerprints. And you can use a Bluetooth to synchronize the fingerprints being recorded and share them over Bluetooth. The inertial sensors in your phone, accelerometer, gyroscope, things like this are used for navigation at the moment and to play games on your phone. But you can use them to determine context very easily within a smartphone. And I hope that many of the contact tracing apps are already making use of the sensors to determine if, for example, a phone is simply left on a table all day long and isn't actually being carried around by a human, because it's very easy to determine if people are walking, running, playing with the phone in their hand, cycling, driving, or if the phone is locked in a locker, not doing anything. And so this helps to add some context to whether the smartphone is being used or not. Barometers are baked into most smartphones today and are used for location applications to determine what floor of a building you're in. The sensitivity is actually really high. You can actually determine if a phone is in a pocket, on the floor, or on a call really easily with a barometer in a standard smartphone. It can measure easily kind of half-meter distances. And so the barometer can be a useful way to help to determine, are these two phones on different floors, even though they can see each other very easily with Bluetooth and so on. And the light sensor on the front of the phone that's used at the moment to dim the display and save your battery life, that can be one of the metrics for indoor-outdoor determination. So the light sensor is a very cheap, very private sensor. It's not like a camera. It doesn't actually see any information like a camera does. It's literally just intensity of light. But it is a flexible enough tool to be able to see if there's 50 hertz or 60 hertz flickering in that light source, i.e. you're being illuminated by a powered light, you're probably indoors, versus you're outdoors and there's no flickering on the light source. And again, in principle, you could use this to compare the measurements on two phones to, again, try and get some understanding as to whether you think the two phones are in a shared space or not, based on whether the light flickering behaviors are identical between the two phones. So in summary, there's a huge amount of information already sitting there on the smartphone untapped. There's some new sensor technologies coming. I think UWB is a really useful tool for this purpose. It'll make a big difference. it has better aspects in terms of privacy concerns compared to people worried about ultrasound being used and the microphone being open. And the quickest bang for buck is that we can generate some fingerprints with the sensor information that's already available on all the phones, and compare fingerprints using the very same channel we use at the moment, the Bluetooth channel. You could exchange fingerprints, check if they match or not, and then destroy them after you've determined whether you think you're in the same space or not based on those sensor fingerprints. And with that, I'll hand over to Joanna and take any questions.
So thank you to all the speakers. A lot of questions are now in the answered column. You can still upvote them there, because some of them, I think, that just means that somebody's responded to them, but there are still some interesting threads. And I'd like to start there with one that was asked by David Bonsall that I would like to, hang on. Oh, Sarah, can you let David talk? To ask the question? No? Okay, so I will read the question out while Sarah fiddles with that. Firstly, the question was, is there a comparison of the distance estimate to what people's memory is from manual contact tracing? Because in order to more directly compare manual contact tracing and these kinds of automated systems. And that question was answered in "We haven't done it" by Karen, but I happen to know that Amanda has been involved, as have I, in an unpublished experiment that did exactly that. So I'm going to suggest that one for Amanda to answer.
Yeah, that's a great question. Joanna, I'm not sure how much I can discuss since the paper's in preparation.
I think just go ahead. I've presented it before. Just go ahead.
Okay. So we did this with some healthcare workers, and I believe we had them keep personal notes using QR codes, from what I remember, and we compared their interactions to the app. And I can't quite remember the results off the top of my head, but I could reach out, or maybe Joanna can chime in if she remembers. But I remember that there were some meaningful discrepancies. I think this is going to be a problem with recall bias in general, where if you're close and you're interacting with someone and you know that person, you're likely going to remember that interaction versus a close interaction with a stranger. Or, if someone said, "Who is in the room?" 12 feet away from you and you were eating lunch and there's a lot of people in the room, I may not remember who that person was. So it's definitely an important issue.
Yeah, maybe I can, I just found a figure, so I'll answer that with the figure myself. But essentially what we did, which sort of aligns very much with, I think, what Karen was saying. Yeah, so these were ground truth, was QR code scans that people going about their daily business in a healthcare worker setting, as Amanda said, were recording who they thought they had an interaction with. And then we were comparing that to what was recorded. And we didn't get to change the bin settings, but we did get to change the weights. And what weights you put on which Bluetooth bins made pretty much no difference, that these kind of accuracy curves are superimposable, but the threshold makes a big difference. And so the Bluetooth is so messy that exactly how you use it had little impact, but that it's all about the threshold. So I think that aligns with Karen's answers and work, but just that we did do it in this kind of comparison with what a human thought they were interacting with in a naturalistic, going about your daily work setting.
So the threshold you're referring to here is the alert threshold rather than the thresholds between the bins? Correct.
That's right.
Yeah.
Yeah, that's how we were able to do this experiment, with relatively little developer access in a real life setting as a closed beta. Sarah, do you have any follow-up? Have you got David Bonsall to talk yet?
Yeah, sorry for the delay. I can go ahead and unmute whoever has the next question for sure.
Okay.
Was that
We'll
David? that
start
you
with
wanted me to do
David
now?
just to see if that's answered his question.
Hi. Yeah, thanks. That's very interesting, and thanks for the extra data. I guess it does answer my question to a point. I think it's important to consider both sort of accuracy, but also, as your colleague mentioned, the sort of sensitivity and the sort of ability to sort of remember anything, not just how accurately you remember that the distance, but also whether or not you remember them at all.
Yeah, and that particular experiment, we didn't actually rely on their memory. We got them to record it in real time. And I think the Swiss team, the Swiss Army had similar experiments very early on when they were working on DP3T. Luca, did you have anything? You turned on your video to add to that? Okay, so the next question, Adam Fowler has asked many questions. I think your top question is about wearables. Sarah, do you want to unmute Adam? And you get to pick one question for now.
Yeah, no problem. I generally can't shut up. So yeah, has anyone considered low-cost wearables as a more reliable mechanism for digital contact tracing or exposure notification? Any testing trials being done on this yet? Thanks.
From memory, I think Singapore provided Bluetooth dongles to people really early on in the pandemic. I think before even the GAIN exposed notification app existed.
They still are doing, yeah.
Yeah. So it's a really good idea for lots of reasons. You know, there were lots of issues early on about the fact that this was all going to be smartphone based, and then you kind of really segregating a section of society. You know, people might not have owned smartphones for various reasons. There's the potential issues of sort of elderly, vulnerable people not having access to smartphones. Perhaps they've got much simpler phones, and so on. So I think it's a good idea. Fundamentally, the chip in the phone is like $1, right? So everyone carrying around $500 devices to use a $1 technology to help keep people safe is kind of a bit strange. So and we're seeing more things like the AirTags and other sort of low cost tracking tags. And you know, once things like this are being mass produced for other purposes, it drives down the cost of being able to provide potentially free tags for people who you know, don't have a smartphone for whatever reason.
Yeah, we've got an open source design. We've been working with the UN on it for developing countries. So we finished electrical testing on it a couple of weeks ago, and we're just building the other prototypes now. Well, there's also a few independent manufacturers doing similar things. Ours is going to be about $15, I think, for a base model, but it's got other sensors on it as well, to things like you know, RGB and IR sensors for light sensors and accelerometers and things.
Yeah, and Andreas has chipped in that the Tile team was looking into it, and I think yeah, those are discussions James Petrie would remember. You know, it's generally a question of, are you doing this as a supplement to the Google Apple system for the vulnerable, or are you, like Singapore, doing it as a replacement? And the issues with replacement is not everyone's going to agree to carry a wearable around with you unless you're an authoritarian regime like Singapore, and there are different sets of issues. With the issue with the supplement primarily is it doesn't get around with any of the problems that have come up with the noisiness. It doesn't, you know, none of the solutions that Ramsey just mentioned get implemented as long as it's a supplement rather than an alternative.
Yeah, so we're making sure that we can support interaction of multiple Bluetooth protocols and multiple PHA backends, so we don't have that issue. I'd also be a bit careful about, you know, throwing around terms about other governments as well, as scientists. But yeah, I mean, we're looking at it because, you know, $1,000 smartphone is just a non-starter. It's like UWB. It's a fantastic technology.
Yeah, I just want to say that you don't need $1,000 smartphone. So we've done extensive testing on White Mountain Apache tribe, and their $60 smartphones work just fine. So to be clear, you know, cheap Androids are cheap these days. Okay, I will want to
Where you
move on.
live,
We've
yeah.
got a lot of questions coming up. I'd like to ask Michael Schuster next.
Can you hear me?
Yes.
Okay, sorry, I was on mute. Forgot about that. Yeah, Ramsey, thanks for your presentation. Very interested. I was just wondering if you had by any chance the opportunity to talk to Apple or Google directly about extending their exposure notification framework to include indoor-outdoor detection, because that would be a huge improvement for, I guess, all the apps would love to have that and this determination. So just a question, if you had any opportunity to talk to them, and if so, if there was any indication if they are willing to think about that. Thanks.
I haven't spoken to them in over a year, actually, I think, and I'll invite Joanna to pick up because I think she's probably had much more recent contact. So I did talk to both entities really early on and let them know some of my background research from many years ago on how to get the best out of Bluetooth. There's some issues about how to make use of the 3 channels that are inside the Bluetooth receiver and some settings to try to help with multipath interference. And one of the things I did notice quite early on in the conversations was just this aspect of them wanting to try to create a technology that became seamlessly part of the phone experience and didn't impact battery life. And so, you know, for me, there's this lever of, oh, I'd rather have a slider bar. So I can, if I want to sacrifice, you know, 10% maybe, you know, to go to a crazy extreme of my battery life, let that be my choice, and I'll just move the slider, and you can have a much, you can have vastly more data, you know, being processed per minute or whatever. But I didn't win that fight, as you can tell. There's no slider bars. But Joanna, you probably know much more than me about how it's evolved in the last year, perhaps.
It hasn't. We are at exactly the same point as that conversation that we were part of, and there have been no modifications to the protocol since then, and no announcements of any intention to enable indoor-outdoor sensing since then. It's the same protocol. We're still on version 2. You know, other things have been modified, but the basic, you know, yeah, nothing in that range. Okay, Justus Bensler is the next question I'd like to take.
Hello, I'm unmuted now?
Yes, you are.
Oh, great. Okay, so yes, my question was inspired also by what Ramsey showed us and explained to us, and it's again about this indoor-outdoor sensoring, and also linked to the question of how many people actually might be in a room and how the air exchange is in a room. So I think very close to an estimation of real aerosol exposure, and that's about carbon dioxide sensors in phones. Is it something that we might expect in the near future?
So a really good question. There's been nothing that I've seen on any technology roadmaps about carbon dioxide sensing coming on phones. Every now and again, you get some really unusual phones built for certain purposes. I remember after the was it Nikojima, the nuclear power station in Japan that didn't quite melt down, but had a rather serious problem a few years ago. There were phones sold in Japan for years after that with Geiger counter sensors in them. And so, you know, it is possible to miniaturize all sorts of interesting things and put them into phones. We could see nitrous oxide detectors and carbon monoxide and carbon detectors in smartphones. I'm sure you'd easily fit them in there. It's the drive from the market to need them. And at the moment, I've not seen anything about air quality sensing going in any smartphone designs.
Thank you.
I'd say something else we've sort of thought about is if public health rather than the tech sector drove that, then you could have beacons for a venue that would contain the carbon dioxide information and send it for the smartphone to hear. So that would be a way, without changing the smartphone design, that the smartphone could get access to that information from an external sensor.
That's a nice approach.
Amanda?
Yeah, can I add one thing to that? I've been really interested in that idea. I think some limitations would be if people are masked or if there's a portable air filter in that space, the CO2 level wouldn't change, but obviously the risks would. So I think if we were to use a CO2 sensor approach, we'd have to somehow account for masking or a rough estimate of how many people would be masked in that space.
Okay, next question, Bill Pugh.
So, a question about the different sensors, ultrasound, ultra wideband. My understanding of the techniques for doing that requires a probe and response between each pair of phones for which you want to measure distance. And so that's reasonably easy to do when you have just 2 phones and you're trying to determine distance. But if, say, you have 10 phones in a room, then each phone is going to need to do a probe and response to every other phone in the room. It's probably going to need to run code to generate the response, unlike Bluetooth, where the broadcasts and advertisements are typically being done by low-level chips. And also, if you have 10 phones in a room and they're all exchanging ultrasound packets, figuring out which response is coming from which device, which rolling proximity indicator, could be quite the challenge. So have you thought about how those sensor modes scale up to multiple devices in terms of being able to resolve individual devices and the power consumption?
Yeah, so I mean, the good news is that this is a totally solved problem. That we've had the solutions to this since World War II, when we first developed radio positioning technologies with transmitters that needed to contain their ID, so you could work out where your bomber was as it flew over different continents. And you can use a lot of well-established methods from all of these things. GPS, another good example. So you typically have an encoding mechanism within the transmission that the other phones know how to decode and measure ID. I think ultra wideband, certainly already there'll be well-established protocols and standards for doing ranging and positioning with UWB. On the ultrasound front, I mean, the guys at Novid, Poe's team, will have solved this problem and developed the way of transmitting some unique identifiers as part of the ultrasonic packet. I mean, you can also simply synchronize events. Bluetooth will still be there. So you can use the lowest power, simplest thing you've got, which is Bluetooth, to do scheduling. So you can schedule that it's my phone's turn to talk to your phone. And that's the ultrasonic ping, and then schedule that it's my phone's turn to talk to Curran next, and then do that ultrasonic ping. So when you've got multiple methods of communication as well, then you can solve some of it with the low power stuff, doing scheduling, and then do the ranging using just the ultrasound or whatever it might be.
But that's still going to require CPUs cycles to be run to do that scheduling, to send out to say, oh, I got a pulse from somebody, I need to send a response. Normally the individual Bluetooth packets, that's not being done by requiring the CPU to come online to measure that. And you're going to be requiring the CPU to be responding to each of these packets and be involved in the scheduling.
It could be. I mean, there's so many different size processors inside smartphones today. You could probably deploy some of this on low power stuff. I mean, a lot of smartphones have what's called the what is it called now? There's low power ARM processors doing motion detection all the time, counting steps. And if your phone rings, you just turn it over and it stops ringing because the accelerometer has detected that you flipped it upside down. So you don't need to fire up 8 cores of 1.5 gigahertz processors just to do something really simple. There's low.
Even firing up 1 core takes, that is a non-trivial power use if you're going to be doing that all the time. I mean, I think a lot of the stuff you proposed could be done if there was like low-level chip support for doing this. You can prototype this using software and just access to the microphone and speaker. But I think to actually do this the way Bluetooth does, it's going to have to be something like in the co-motion chips or some sort of low-level chips. I think bringing in the CPU is, I would love to see an experiment on whether or not you could do that, but I just think it is going to be significantly higher than what Bluetooth uses.
Well, the UWB chips are already designed to do ranging measurements. But
most of the protocols are pairwise.
Yeah.
Right, and not to simultaneously measure to all pairs of phones.
Yeah, I mean the person with half of the answer to this question is Po Shen Lo from Novid, right? So
okay.
He knows what the power draw is of the Novid app and how many different users at once it can answer. So I'm sure we can reach out to him on Twitter and get the answer.
Thank you.
Okay, I think there's one more upvoted question from Mike Worth. Other than that, I also want to make sure I give the three panelists a chance to ask each other questions. Are there any burning questions you have of one another? Otherwise, last question will be Mike's.
Okay, hi Ramsey.
Hey.
Quick question. There was a flurry of interest by Bluetooth mesh lighting manufacturers early last year, in the sense that does Bluetooth mesh lighting become ubiquitous enough, and could it be useful as a fabric for helping pairs of users estimate their interdistance?
So, sorry, you're saying Bluetooth mesh lighting?
Yes. So in other words, a Bluetooth mesh lighting network that's implemented with Bluetooth in every light bulb in a large building.
Yep.
And, then you get into location privacy issues, but nonetheless use it as just an intermediary.
Well, it would it definitely help if there were other sources in your area, each making measurements to the phones, as opposed to just a direct measurement between the two phones. But then you're starting to get into the location tracking side of things, and there might be sort of privacy aspects. But the best way to use, I think, what you're describing is to effectively use the infrastructure to track the phones, and then be measuring their proximity that way. But a simple rule of thumb for sensor fusion and location and positioning is the more measurements, the merrier. So the simplest answer is yes. If there's more measurements in the environment, then you're going to be able to do a better job of working out what's going on.
I have a thought to add to that based on other systems. The more measurements, the merrier, but if the measurements that are sort of baked into the network, if the reason for that light mesh to exist is location oriented, then it's more likely that that location data will continue to be correct and relevant. But if the location data is sort of piggybacking on a network whose true purpose is to provide connectivity or some other state of awareness, then when you deploy these things in buildings, eventually you get bit rot. Someone goes and moves something to another room to fix an immediate need. They don't update the location information, and you end up with garbage in your system because humans are involved. Unless you can really intertwine those goals of the system to deliver this and that together. So I think technologically, it's an interesting thing to pursue. But even if you were okay with the privacy aspects of it, I think that it would be difficult to keep humans motivated to maintain it when we're not in a state of high emergency.
Well, part of the goal of some of these systems is to be self-adapting. So you can move the lights around and the system still works. So lots of design parameters here.
Yeah.
Okay, finally, last questions before we add up is, do the panelists have questions for each other? Or Luca, you can jump in too.
To say I'm very excited by some of the things that Ramsey suggested in terms of sensor fusion and sensor fingerprinting. A lot of different directions to go there. I don't have questions off the top of my head, but I'm definitely going to be looking more of this up.
yeah, I think the imagination of knowing what is possible is, you know, just the digital contact tracing is possible at all, how much better it could be, how many, you know, the degree to which we could fight disease. I think, you know, what we want to do is inspire with the possible, not be satisfied in science for the status quo.
Yeah, I would love to have a better, you know, if we could have a heat map for the probability of infection. If we could have one, that would be lovely. I'd settle for 6 or a dozen, you know, based on different conditions. And then if we could include information about mask wearing and CO2, air changes, et cetera, we could do better. But it comes back to, like, let's not lose sight of the fact that we really are interested in estimating the risk of infection and not just distance.
And on that, I will just call out that Luca from the UK and Justus, who asked a question earlier from Germany, you guys are the ones with the data. And we're at the edge of our seats waiting to see what you find. The data on actual infection.
As you know, there's not so much to find. The data is limited, but yeah, maybe just this something.
We know you have some. We know something is possible.
There's something, not that much. Not as much as we would like. One interesting question about all these developments is how much it will be possible to learn actually about the disease. So this is something that comes back to the origin of digital contact tracing. So it's interesting to use all these tools, of course, to get a better estimate of the risk. But it's also useful to have these tools available in order to do the opposite and try to learn about the ever-changing epidemiological features, especially in the presence of variants.
It's ridiculous that we don't know asymptomatic versus symptomatic transmission at this stage of the pandemic. And if this system had been configured to make it a little easier to study, we'd have that, and we'd know how it changed with vaccination, and we'd know how it changed with Delta strain, and we'd know what degree of danger is posed by vaccinated asymptomatic infections if the system had been configured to more easily allow analytics. And the decision was made that the system was not to be used to study COVID, but merely to contact trace it, means we don't have answers to fundamental questions that go a lot beyond digital contact tracing.
But many of these questions could be useful for the near future. Possibly, I mean, it's expected that new variants will keep traveling around the globe, if not in Western countries, most probably in the rest of the world for years to come. So some of these tools could come handy, even if maybe not so much in Europe or in the US, maybe in third world countries, to understand a bit faster about how the disease is spreading and if there are different variants.
Yeah, I mean, work like your analyses, Luca, that were based on extraordinarily intensive manual contact tracing in the earlier days of the pandemic. And that's where we got our basic parameters on incubation periods and infectious periods and so on. And nobody's doing that for an endemic disease. It's not going to be done. And so this technology is actually the only way, I think, that we're going to end up learning, you know, or a version of this technology that permits it is probably the only way we're going to end up learning the basic parameters of disease transmission without intensive contact tracing of the sort virtually nobody does. Manual contact tracing, that is.
I think it's a good point to stop here.
Yes.
We have more than 20 minutes.
Sorry, yes. Thank you all for coming. September 28th, we'll talk about presence tracing and different protocols for that. Thank you all for joining us.
Thank you very much.
Thank you very much to all the presenters.
Thank you, everyone.
Awesome talks. Thank you.